Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will discuss about the full wave rectifier and its various parameters. This topic is meant for class 12 students of CBSE, ISE and different state boards. The topic covered here will also be found useful for BSc Physics and Electronics students and also for various competitive exams like NEET and JEE Mains. The complete note of the topic is given here for our convenience. I hope you enjoy going through it. Now let us come to the topic. A full wave rectifier circuit is shown in figure 1 here. So this is your transformer. This is the primary coil and this is your secondary coil. This is center tapped. That means the middle of this is earthed. We are using two diodes here. This is the one diode and this is another diode here. Okay. So alternately, the ends of the transformer becomes positive and negative. This is upper end is we have termed A, the middle one is B, and the lower one is termed as C. Okay. So see how the connection is made. From A, we have a diode D1 connected here. This is the positive end of the diode, and this is the negative end. Similarly, in diode D2, this is the positive end and this is the negative end. From here, we have a resistance here. The other end of the resistance is connected to the middle point O, middle point B here. 0 stands for 0 voltage here. This is point is grounded here. Okay. So suppose when the upper end of the transformer secondary is positive, that is end A is positive, then this diode D1 is now forward biased because its positive end is connected to the positive potential here. So current flows through diode D1. Okay, this is shown by the blue line. This is the line. So current flows through diode D1, passes through the resistor from the top end to the bottom end, and then goes along this direction and then along this. So this circuit is completed. During the first half of the cycle, when the upper end of the transformer secondary is positive, current flows through the diode D1 in this direction. Okay, and through the resistor, the current flows from its top end to the bottom end. Okay, during this first half, the lower diode D2 is in the cutoff stage because the lower end of the transformer secondary is negative. So negative potential is connected to the positive end of the diode. So this remains cut off. So during the first half cycle, the diode D2 doesn't conduct. So there is no current flow through the diode D2. Current flows only through diode D1. Clear? The next half cycle, when the upper end becomes negative and the lower end of the transformer secondary becomes positive, current flows through the diode D2 because the positive end of the diode is connected to the positive potential here. So current flows through this diode along this direction. The current flows through this along this direction. The current does not take this path because this diode is non-conducting. Current takes the right turn here and flows through the resistor RL from its top end to the bottom end, and then again it follows this path and the circuit is now completed. So we see that in each half of the alternating cycle, only one diode conducts and the other remains cut off. The current flows in both the halves through the resistor from its top end to the bottom end. Clear? So this is how the current flows in the circuit. In the resistor, it flows in the same direction all the time. At one half cycle, diode D1 conducts, while diode D2 remains cut off, and in the other half cycle, diode D2 conducts and the diode D1 remains cut off. Clear? So this is what I have written here in detail. Clear? So we just see that the current flows through the load resistance in the same direction during the entire cycle of the input signal, and each diode conducts on opposite half cycles of the input signal, resulting in a load current of half sine pulses. The different currents and voltages waveforms are shown in figure 2 here. So see, in figure 2a, we have shown you the input voltage. This is full cycle. Okay. We are showing you here the full wave, the input to the transformer secondary. Figure 2b shows you the voltage across RL and the current through RL. Since the current flows through the resistor all the time, whether through diode D1 or through diode D2, current flows through the resistor all the time. And because the input potential increases and decreases, the output potential also increases and decreases. Clear? Since the current rises and falls, current is now unidirectional. Current flows in the same direction through the circuit in the load from its top end to the bottom end. So current flows through the resistor in the same direction. So if you multiply the value of the current by resistor, you get the potential across the resistance. So this is the graph of the VR, the potential across the load resistance. And this is by pink color, we have shown you the current through the load resistor. Clear? Now, figure 2c shows you the current through the diode D1. We have seen that diode D1 conducts only through half cycle. So in the first half cycle, it conducts. In the other half cycle, diode D1 becomes cut off. There is no current through the diode D1. Clear? Then again, it becomes, upper end becomes positive, diode D1 conducts. So this is the waveform of current through the diode D1. So when the diode D1 conducts, diode D2 remains cut off. So when diode D1 conducts during this period, during the same period, diode D2 is cut off. When diode D1 is cut off here, diode D2 conducts. When diode D1 again conducts, diode D2 is cut off, and the process continues. So whenever one diode conducts, other is cut off. Okay? So they conduct on alternate half cycles. In figure 2e, we have shown the voltage across the diode D1. Okay? When the diode D1 is not conducting, when D1 is cut off, the potential across this is simply minus 2 Vm. Why Vm? 2 Vm? We have potential between point A to point B, Vm, and point B to point C, this is Vm. So this is 2 Vm. So entire potential drops across the diode D1, which is non-conducting. Similarly, when diode D2 is non-conducting, this is the voltage across diode D2. When this is not conducting, when diode D1 conducts. So in the first half cycle, diode D1 conducts and D2 is non-conducting. So this is the waveform of the potential across the diode D2, and this is the waveform for potential across the diode D1 when diode D2 is conducting. We assume the two diodes to be ideal. क्या मतलब इसका? इसका मतलब है कि there is no voltage drop across the diode when the current flows through it. Okay? so that there is no barrier potential also. आप ये भी बोल सकते हैं उसके क्रॉस कोई barrier potential नहीं है, ठीक है ना? So that when a current flows through it, there is no potential drop across the diode itself. हम देख चुके हैं when Vi is equal to Vm sin omega t, then current is equal to Im sin omega t. तो मान लेते हैं कि पहला डायोड जो हमारा है ऊपर में D1 उससे करंट फ्लो हो रहा है एंड दैट करंट इज ID1 इज Im sin omega t. ये कैसे हुआ? हमारे पास है Vi इज इक्वल टू Vm sin omega t, इसलिए ID1 कितना होगा? Vi अपॉन कितना रेजिस्टेंस सर्किट में है? कुल रेजिस्टेंस है हमारा RL, ठीक है? तो दिस इज Vi अपॉन RL, सो दिस इज Vm upon RL sin omega t. This is the maximum value of voltage Vm. RL is the resistance in circuit because we have neglected the resistance of the diode. Okay, so this is the maximum value of current within the bracket. This is nothing but Im. So this is Im sin omega t. Okay, so when the upper diode conducts, the lower diode remains cut off. So ID2 is 0. There is no current flow through the second diode. So this equation is valid when omega t is between 0 and pi. Omega t lies between 0 and pi. In the second half cycle, the upper diode is cut off, but the current flows through the lower diode. So ID2 is minus Im sin omega t, and this is valid for omega t lying between pi and 2 pi. This is okay? So we now come to the mathematical analysis of the full wave rectifier circuit. We will first find out the average or DC value of the current. We have IDC. यहाँ हम लोगों ने इसका वैल्यू निकाला है हाफ वेव रेक्टिफायर केस में भी, यहाँ भी निकालते हैं. IDC is 1/2 pi 0 to 2 pi ID1 d omega t. This is for the current through the first diode plus 1/2 pi integral from 0 to 2 pi ID2 d omega t. This is the current through the second diode. अब देखिए फर्स्ट डायोड में करंट फ्लो हो रहा है 0 से पाई के बीच में, ठीक है? सेकंड डायोड में करंट फ्लो हो रहा है पाई से 2 पाई के बीच में. सो आई ब्रेकअप दिस लिमिट इनटू 2 पार्ट्स. देखिए फर्स्ट केस के लिए ये जो हमारा है इसको हमने मार दिया है इस पूरे में, ठीक है? एंड दिस पार्ट इज इक्वल टू this part. Okay, this is for the current flow through diode D2 here. Now the current through the diode D1 flows only for omega t lying between 0 and pi. So we divide this integral into two parts, from 0 to pi and then pi to 2 pi. Similarly, diode D2 conducts only for the period when omega t lies between pi and 2 pi. So we divide this integral into two parts, from 0 to pi and then pi to 2 pi. So this becomes this one and this becomes this one. So the first part gives you 1/2 pi integral from 0 to pi ID1 d omega t plus pi to 2 pi integral का लिमिट है ID1 d omega t. So and for the second part, this is 1/2 pi integral from 0 to pi ID2 d omega t plus integral from pi to 2 pi ID2 d omega t. Now this term is 0, okay, because current in the period pi to pi is 0 through D1 diode. So this is 0. Similarly, for diode D2, current is 0 for the period 0 to pi. So this part gives you 0 here. Okay. So we are left with IDC equal to 1/2 pi integral from 0 to pi Im sin omega t d omega t minus 1/2 pi integral from pi to 2 pi Im sin omega t d omega t. So when integrated, this gives you, first term gives you Im by pi. The second term also gives you Im by pi. So this is equal to IDC equal to 2Im by pi. Okay. RMS value of current. We have IRMS square is 1 upon 2 pi integral from 0 to 2 pi I d1 square d omega t plus 1 by 2 pi integral from 0 to 2 pi I d2 square d omega t. This is for the current flow through diode D1 and this is for current flow through diode D2. So this much is clear. So current flow through the diode D1 takes place only for the period when omega t varies between 0 and pi. तो हमने पूरे इंटरवल को 0 से पाई और पाई से 2 पाई के बीच में बांट दिया है for the current flow through diode D1. And similarly, we have divided the current flow through diode D2 over the interval 0 to pi and pi to 2 pi. Pi से 2 pi के बीच में diode D1 से current 0 है. So this is 0 here. ठीक है? This is 0 here. In case of diode D2, this part is 0. So this part is 0 here. Okay? Second part gives you I d2 square as Im square sin square omega t d omega t. Clear? So the first part, when integrated over this period, gives you Im square by 2 pi into pi by 2. And this part gives you also Im square by 2 pi into 0 plus pi by 2. If you take the sum, this gives you Im square by 2. So I RMS is equal to Im by root over 2. Thus, if Rf be the forward resistance of the diode, then the maximum, average, and the RMS values of the voltage across the load resistance RL are given by the following expressions. The maximum voltage across the load. This is V maximum, is I maximum into RL. Im is Vm upon Rf plus RL. We have taken here into account the forward resistance of the diode Rf, which is the resistance the diode offers when it is conducting the current in the forward direction. So this is V maximum equal to Vm upon 1 plus Rf by RL. Okay. The second is the average or DC voltage across the load. This is VDC is equal to IDC into RL. IDC, as we have seen, is 2 pi Im by pi into RL. So this is 2 by pi. Put the value of Im here. This is Vm upon RL plus Rf into RL. So this gives you VDC as 2 Vm by pi into 1 plus Rf upon RL. The third is the RMS value of voltage across the load. So this is VRMS is IRMS into RL. Put the value of IRMS is Im by root 2 into RL. Now put the value of Im. Value of Im is Vm upon Rf plus RL. And simplify with this RL. This gives you value as Vm by root over 2 into 1 plus Rf by RL. Next comes your ripple factor. We have seen in half rectifier how the ripple factor is defined and what is the formula for it. The ripple factor is given by R equal to root over I RMS upon IDC whole square minus 1. Put the value of I RMS for full wave rectifier and the value of IDC for full wave rectifier. So this is Im by root 2 upon 2 Im by pi. And the whole square of this, okay, minus 1. So this gives you the value as ripple factor R is equal to 0.482. Next is peak inverse voltage. वो voltage जो नॉन कंडक्टिंग डायोड के क्रॉस लगता है, this is known as peak inverse voltage, maximum voltage that is applied across the non-conducting diode. So when the diode D2 is non-conducting, Maximum reverse voltage across it due to the transformer secondary is Vm. At the same time, the diode D1 conducts and the current flows through the resistance RL, developing a voltage drop Vm across it. This voltage drop across the resistance RL is in series with the reverse voltage across the non-conducting diode D2. Thus, the total reverse voltage that occurs across the non-conducting diode is 2Vm. Okay. मैक्सिमम रिवर्स वोल्टेज जो नॉन कंडक्टिंग स्टेज में डायोड के क्रॉस लगता है दैट इज नोन एज योर पीक इनवर्स वोल्टेज. In case of half wave rectifier, this is Vm. In case of a full wave rectifier, this comes out to be 2Vm. Next is your rectifier efficiency. The DC power output in a full wave rectifier is PDC is IDC square into RL. Put the value of IDC, this is 2Im by pi whole square into RL. So this is 4 by pi square into Vm square upon Ra plus RL whole square. Here we have put the value of Im and then squared it into RL. And the AC power from the transformer secondary is PAC is I RMS square into Ra plus RL. Put the value of IRMS, this is Im by root 2 into whole square into Ra plus RL. For Im, we put here Vm by Rf plus RL. Okay? This is Vm by Rf plus RL whole square. Okay? And this Rf plus RL is appearing here. So we have PAC equal to Vm square by 2 times Rf plus RL. And therefore, the rectifier efficiency, which is defined as the ratio of PDC upon PAC, is equal to this much. Okay, so eta comes out to be 81.2 upon 1 plus Ra by RL percentage. Here we have simply put the value of PDC and PAC to get the result here. We just see that the rectifier efficiency of a full wave rectifier is exactly twice that of a half wave rectifier under identical condition. If the diode is ideal, so that Rf equal to 0, the maximum efficiency of a full wave rectifier is 81.2%. Next comes transformer utilization factor. The average transformer utilization factor in case of a full wave rectifier is determined by considering the primary and secondary windings separately. This yields a value of 0.693 as compared to 0.287 for a half wave rectifier. Moreover, since the current flows in the two halves of the secondary windings in opposite directions, the problem due to the DC saturation of flux in the core is automatically eliminated. So this is all about the operation of a full wave rectifier and its various parameters. I assume that you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. So thank you for watching. See you next time with some other topic of interest. Till then, goodbye.